Okay. We're up about 5,000 feet. AGL. Well, you talk about clearing turn being easy at this point. See everything. No traffic on the scope. Got one about 25 miles away on the opposite direction. We'll start slowing up. I'm actually gonna start flaps and then do clean. We're gonna go straight third notch. Well, we should have already been stalling. Power on stall. Wow. CFD seems to indicate 8. I saw 43 and we still had it. Trying to get that tail down. Wow. Recovered within 50 feet. So that was a gain of 7. Let's go into climb, 8,500. Alright, good job. There it is. 48 miles an hour, hard stall, good recovery, lost 200 feet. That's a stall. Drop the right wing. Lost 200 feet. That's a little over 10 miles an hour less, and I'm gonna take one off that. So she's stalling clean at 48, and she was stalling clean at 58. Power on. Broken 39. Only lost 100 feet, call it 120 feet, flaps down. So it's actually slightly better than what I was allowing on a power on. We'll fly out this direction. We're gonna go ahead and get down back to our target altitude. Get in a good dive, hit 162 miles an hour, getting down to 8,500 feet. So this has totally changed our attitude. It's essentially raised, flaps are all the way down. We're having to hold negative pressure, negative lift on the tail, substantially more. We're in a slight nose down attitude in order to maintain altitude and keep from climbing. Airspeed is indicating that CFD, as usual, is probably correct. Seem to have picked up about a 2 mile an hour gain. I mean, there can be a lot of variables, so that's not at all conclusive. Typically when you're using good CFD, like, praise the Lord, what I have access to, yeah. We're at the same density altitude. I conducted this clean 2 days ago, and we are faster, which is probably going to be a phenomenon you'll only really see with a wing like this, probably more of such a high lift airfoil. It's laminar. So it's really interesting. I'm having to almost recalibrate everything, and I'm probably going to have to do my flight attitude for my Adahars unit recalibrated, because it basically shows me, I mean, the VSI is all correct, but you know, your horizon indicator shows you in a dive slightly, which, you know, it's not, you know, if you understand Garmin's, that's not a parallax adjustment, which is often misunderstood. But it should show you, you know, the bubble should be on the horizon. And so it keeps having to correct, you know. So I just recalibrated that. And I'm surprised. I really didn't think about that. I didn't plan on that. So that's been a very interesting development. More lift and flat level flight. Roof Falls traffic is on short final for 17 Roof Falls. Wish the wind wasn't blowing so hard. I'd kind of like to take this thing into the grass, but for checking our calibrations, I'm going to keep it right here. she lands quite a bit different. I got to calibrate my approach as well now, because boy has it changed. I mean, I was thinking, okay, you know, 5-6 miles an hour, but drop 11 miles per hour any configuration off your stall, and does that change things? But what's funny is it didn't really change the angle of attack. It's interesting. It rocked the wing forward, essentially almost giving it as though you gave it more camber. So I come down in the same configuration I used to, just slower. A little scary because you're like, whoa, 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 that's too slow. That's the iffy part. All right. It's like crosswind takeoff. Go ahead and start with flaps deployed. See what happens. That's scary. I was pulled back about 3 or 4 inches on the manifold pressure on account of I just don't want to work the engine any harder than I have to. I'm really just trying to check stall angles, not takeoff performance. But it has changed significantly. A little bit scary. She was flying long time before I was ready. I'm going to keep my approach speed the same. I'll just bleed it off. It is just scary to be sinking down over these hangars at 50 miles an hour. Boy, can you make that soft. Woo, that's fun, boys and girls. That's pretty nuts, but I'm gonna practice that a lot more before I do it in the real world. It's nice to just kind of gently roll forward. Yeah, see, no flaps takeoff is about like it used to be with flaps. Just to roll forward, you know, keep the engine shoved in about 80%. Don't have to tax it. I mean, when you got a runway long enough like this, I don't like to go max power. That's pretty wild.
Okay, so here there's several things you have to look at, but this is the exact airfoil down to practically the very thousandth of an inch, literally, in CAD, and including our VGs correctly sized and spaced. So I'm going to cut through a lot of this. This was hundreds of tests, and CFD, it does it pretty quickly, but it still took the better part of a couple of days of just 8 to 10 hours straight of running different tests. What is interesting is you are almost always stick neutral on this wing, no matter what you were doing. Once we added the VGs, especially right here where we did, which is essentially just behind 3%. We're sitting at about, depending on how you measure it, but it's about 3.5%, and here's 5. So 5% is basically right ahead of the spar, and it's not bad. In fact, it's pretty good, but it does create more drag than further forward. So guys that know anything about placing VGs on wings will traditionally tell you the further forward, you get on this thing and you get into that high pressure air, then the more drag you're going to pick up. But as you can see here, this represents velocity. This air back here is moving at about 20 miles per hour faster than this air here. This here is about 50 miles an hour slower. This green line here, that's about 25 miles per hour slower. And so the VGs are increasing, airspeed you see here. But if we remove the VGs, which we'll do here in a minute, and you analyze that, we're basically ahead of the really fast air. So all I did is I wanted to creep the VGs up and get out of the really fast air, and but I wasn't willing to chase and get up into this really, really slow air. Although there was a benefit, even in stall, but it's so unrealistic. It's just so unrealistic. With your VGs that high, your wing, this wing, in CFD stayed glued, above 30 degrees. And in this position, it does too. but it did have more lift at that attitude when the VGs went even further forward. And so you're talking like 1.8 to 1.5% chord was probably the maximum lift and stall angle. But that's so unrealistic. So, you know, just kind of rein back into reality here. This is what, all things considered, after hundreds of tests, I settled on. So when you look at this right here, you'll see that this is pretty smooth. We don't really have any disturbances in the air, and this is just velocity. So this is our first disturbance. You can already start to see the swirling taking effect as it's trailing back over the wing, and especially when we get back here, they begin to get tighter and tighter, and they extend practically all the way to the trailing edge of the aileron. And so that placement that I settled on gave that effect the best. And so what winds up happening is we have, just for a plot, we've got a drag force in pounds, and then we have lift force right here for this section. I have 15 such sections. This test represents a sample of a wing area. I have 15 such wing areas combined between the two wings that are relatively undisturbed. I say relatively, completely undisturbed airflow. And so what had slightly disturbed airflow, I just ignored. And so combined, you know, the average out, you essentially have 7.5 of these such sections per side. And so I analyzed them, you know, like that. Now VG's removed, same exact test. The results are in. For the purposes of making this video, as far as the resolution, I'm only down to tenths of force pounds as in lift and drag instead of hundredths. So the actual numbers are 0.39, but here it's just going to show to the tenth, so it's going to be 0.4. So as you can see, VG's removed now. We have an increase of 0.4 tenths of a pound in drag and a decrease in lift of 1 pound. That is per section. I have 15 such undisturbed sections. The disturbed sections can be analyzed, but that I'm not even going to bother, because the point of this is to figure out the ideal, if there is one, location for the VGs. Turns out there probably is ideal location. So if we go in here and do a cut pattern, what you'll see, which influenced initially began settling in the location for the VGs, you see a bubble right here. So this air right here, indicated airspeed, sea level, we're in 115 mile per hour cruise. This air right here that you see in this bubble, it's a little swirly bubble where the air is climbing up off of that nose, but the oncoming air is mashing it back down. And so you're kind of getting this little number. And so on one of the tests, I actually kind of targeted that, and I was like, well, this is either going to be really bad or it's going to be amazing or weird, but you know, how can you not? And you can see you have another one forming back here, and slightly at about 5%. So, you know, where we settled on, what we're doing is we're just scooping into this one, and that's the location I settled on. Once you get back here to 5%, it's just all fast air. So we're basically kind of scooping into this slower air right here that's moving at about 115 miles an hour. So essentially it's already climbing the wing, but there's a bubble right there that we kind of scooped into, and it's not moving any faster than the oncoming air. Right here, it's actually moving at 93 miles an hour. That little blue spot right there is 93 miles an hour. When you bring these BGs at this spacing, which is 3.5 inch spacing, up into that bubble, you get a even greater reduction in the drag, about a 40% less drag per VG, simply because of that air. And I figured it may render the VGs less effective. It made them actually even more so. And it made the wing, you know, the wing as it is in any flying condition that I can get into on approach, it's practically unstallable, because you just go into a sink. And so that's where the determining, you know, location for this came in, is you move it further forward. I was, in fact, because you're combing air, you know, at 31 degree angle of attack, and the wing would not stall at that. But you can't get the wing there realistically in the real world, and it aesthetically looked crazy. So my decision making was as simple as that. So once you're holding, laminating the airflow fully over the ailerons and flaps at like 30 to 31 degrees, that's so unrealistic. And I was wondering if I was even going to get the plane into that attitude, and you can, but it takes a lot of power. And with no flaps, you basically just have to, get up a good head of steam and just point it at the sun and just wait until the airspeed hits 38 to stall, because you physically can't get the airplane or hold the airplane realistically in a 30-degree angle of attack on the wings. And so it's just not realistic. You certainly couldn't do it for landing purposes. It'd be dangerous as all get out. So what we wound up with really is a wing that just won't stall. And when it does, it just noses down. Okay, so this is a 30-degree angle of attack versus chord line parallel with the earth. And we are generating 1,800 pounds of lift using the 15 sections. So this is at 45 miles an hour. That is the speed which it makes to maintain that. So you can see how accurate CFD is compared to reality, because we can maintain altitude and 5 miles an hour above stall at that. Past that, you're really going to sink. So the interesting thing about the spacing is that you can see the vortices coming off these VGs on this cut right here. And so you can see them changing shape. Here, especially if you watch this one, they get more dynamic the further back you go, but this is at a 3.5-inch spacing. There's never a point where you don't have colliding vortices going down the wing. They're always at that spacing. And so spacing was as simple as that. You just, get them as wide as you can, because my thinking was you didn't want too many of them. So, past 2.5, there were negative gains, and past 3.5, perceptible gaps began to open up between them once you got, 4 inches and upwards. And so 3.5 seems to be about right. And then, I did 3.5 inches for most of the wing and outer near the tips, the last few feet went to 60, but even analyze that in CFD, and it just frankly really doesn't matter. You'd probably be just fine going 3.5 the whole length. My thinking was, the conventional thinking, like, see, you either delete some on the inside or you put more of them on the outside. It is slightly more effective at 2.5, but in reality, as a net gain, especially what's going on with the wingtips, you could just slap them on at 3.5 and call it good. But that is how spacing was determined. So it was actually really simple. I mean, it took maybe all of an hour and a half with just a few tests, and you could just run across those generators. And when you saw those vortices disappear, I didn't have to get up, in an airplane with all kinds of yarn and test all these different spacings in 1/2-inch increments. It was pretty simple. So that's how I determined spacing. So here is the VGs simply removed, and you can see we are in a hard full-on stall. And so we're just taking this wing section here, and so we've got a reduction from 125 pounds of lift, this is at 45 miles an hour, to 80 pounds of lift. We also had a reduction in drag, and that's because of the backside of that. So when you're coming into landing and short takeoff and landing, as long as you have a lot of horsepower, the drag isn't a bad thing. You want high drag and high lift. Low drag and high lift is a little bit of kind of what I got right now with this setup on approach, because it's a really low drag airplane and it makes a lot of lift. So you got to put, some negative lift back in the tail. So for this airfoil, there's a magic range. But other than, targeting those little bubble locations that we were looking at right there, there's not really a magic spot. And the magic locations are, of no consequence to me. And the net result was an 11 mile per hour reduction in stall speed and a slight increase in cruise speed. And I understand the increase in cruise speed. I'm surprised. And by the way, that increase does go away the further back they go. which makes sense. So when you place the VGs back here in this higher speed air, of course, the drag increases. You technically, though, have to go in and look at pressure too, because there can be some faster air, but you'll see a little low pressure bubble maybe on that leading edge. And so if it's like half the pressure, low pressure bubble, then the fact that the air is moving faster, but if it's half the pressure, you could actually have less drag in that location. But to really get a good trip, you want, you know, ambient pressure or higher, but you don't actually need to be in the fast air. So it was kind of a win-win. It did, though, make, I'm going to have to really work on my landing technique because it changed everything as far as that. You can now come in like the Cubs do, high angle of attack, dragging really slow, which is another skill altogether. The end result is this airplane with this airfoil I could find my target spot and come down. I knew exactly when the wing was going to stall. I'd pick my spot, come up right above the ground, flare the wing would stall exactly when it's supposed to. You plopped right on the ground and the whole world stood up and cheered. Now, you come down a full 10 miles an hour slower on approach. You flare 10 miles an hour slower, except the wing won't stall. So you plop right on the ground and the wing is still flying. And the only way you can make it quit is if you spoil the lift by dumping the flaps. And so it's different because this wing, you sitting on the ground, you can't stall it. And you start rolling down the runway and it's flying almost immediately. And so I'm used to stalling a plane out right where I want it, which is a very different technique than a lot of the Cub guys do, in which case they're kind of in the same scenario. Their wing doesn't necessarily stall, and the only way you can do it is if you do the great big old high angle of attack, plop it on the mains technique, which that works. And so it's just going to take some getting used to because it is, it does fly much more like a Cub. All the way around, it was definitely a win-win, and it was far more effective than I imagined, but it definitely matched what CFD predicted as far as the angle of attack and increasing lift and moving the center of lift and all that.